Hello everyone. Today I'd like to talk about the linearly independent or linearly dependent vectors. So the very important concept is that if you are dealing with R2 or a two-dimensional vector space, then you can have at most two linearly independent vectors. So similarly, if you are dealing with R3 or three-dimensional vector space, you can have most three independent vectors. So don't get me wrong, if you are randomly given three vectors in R3, it doesn't mean that they must be linearly independent. You still have to check. But if you have four vectors in R3, then they must be linearly dependent. Okay? So give you a specific example. Now you are dealing with R2 two-dimensional vector space, but you have three vectors like this one. The first one is 1, 0, the second one 0, 1, the third one 2, 3. So because this is R2 and you have three vectors, they must be linearly dependent. Okay? So there are two ways to check their linear dependence. The first one, you can see that the 2, 3 is simply the linear combination of the first and the second one. Okay? So that's why they are linearly dependent. The other way to check is to use the definition. So we have to show that A1 times the very first vector plus A2 times the second one plus A3 times the third one equals 0, or simply a 0 vector. Okay? So then you end up with two equations, A1 plus 2A3 equals 0, and A2 plus 3A3 equals 0. All right? So let's give you A3 equals negative A1 divided by 2, right? Or I should express it in another way. A1 equals negative 2 times A3. And A2 equals negative 3 times A3. Okay? So as you can see, A3 will be a free variable. After you assign a value to A3, A1 and A2 are determined, right? So for example, if A3 equals 1, then A1 equals negative 2, and A2 equals negative 3, right? Or, for example, if you assign A3 equals 2, then A1 will be negative 4, and A2 will be negative 6. So as you can see, this equation will have an infinite number of solutions. By definition, these three vectors are linearly dependent. Okay? All right. So similarly, I'll give you another example in R3. So how about I have 1, 0, 2, 2, 1, 1, 3, negative 1, negative 1, and the square root of 2, and 1 over 4, 1 over 5. Okay? Now, these vectors are in three dimensions, but you have four vectors. So we immediately know that they must be linearly dependent without carrying out the definition. All right? Okay. So I'd like to give you more examples. How about this one? In R3, you have 1, 2, 4, 2, 0, 0, 0, 1, 2. Okay, you have exactly three vectors. Okay? So there is no conclusion you can make immediately after you have observed these three vectors. So to determine their linearly dependence, we can use the definition A1 times 1, 2, 4 plus A2 times 2, 0, 0 plus A3 times 0, 1, 2 equals 0, 0, 0. Okay? So this gives you three equations. A1 plus 2A2 equals 0. 2A1 plus A3 equals 0. And then finally, 4A1 plus 2A3 equals 0. Okay? So you notice that the last two are equivalent because you can simply multiply by 2 and you get the other equation. So you have only two equations to deal with. And these two equations give you the A2 can be expressed in terms of A1 and A3 can also express in terms of A1. Okay? So again, A1 is a free variable. After A1 has been determined, A2 and A3 can be determined accordingly. So these equations will have an infinite number of solutions. Therefore, these three vectors are linearly dependent. Okay? However, in this example, actually you don't have to carry out the definition because you notice that you can multiply the second vector by 1, -1 over 2. Okay? So I will put a note here. So now you have 1, 2, 4, 2, 0, 0, 0, 1, 2. And then you multiply the second one by -1, 2. You end up with 0, 2, 4. 2, 0, 0, the second one and the third one. Okay? And you notice that the first one is equal to the -2 of the third one, right? So you end up with 0, 0, 0, 2, 0, 0, and 0, 1, 2. So apparently, these three vectors are linearly dependent. And we conclude that the original set is linearly dependent. The reason behind this is that we have carried out only the linear combinations. Okay? So by carrying out linear combinations, you will not change their property in terms of linear dependence. So after, no matter how many linear combinations you have tried, if you end up with linearly independent vectors, then the original ones are linearly independent. And similarly, if you have carried out several linear combinations, you end up with linear dependent vectors. Then it implies that the original vectors are linearly dependent vectors. Okay? So this is how you can determine their dependence in terms of linear combinations. So let me give you another example to help you better understand this concept. So let's say that you are dealing with 4 dimensions. The first vector is 1, 0, 1, 2. The second one is 2, 0, 0, 0. And the third one will be 0, 0, 2, 4. Okay? So of course, you can carry out the definition if you like. But now I like to use an easier way to do so. So first, I notice that I can remove the first component by multiplying the second one with -1 over 2. So I end up with 0, 0, 1, 2. And 2, 0, 0, 0. 0, 0, 2, 4. And this is the first linear combination I have carried out. And then I can do a similar procedure by multiplying the first vector with -2. So I end up with 0, 0, 1, 2, 2, 0, 0, 0, and 0, 0, 0, 0. Okay? So apparently, this one, the zero vector, will be redundant. And of course, these three are linearly dependent. Okay? So I didn't carry out any definition. I simply determine their dependence by linear combinations. Okay? Alright, so I hope these examples can help you better understand the concept of their dependence, linear dependence or linear independence.